Hello, I am Professor N.B. Hulle. In this video, we will try to understand interfacing of 2x16 character LCD with Spartan 3E FPGA. I have the Spartan 3E starter development board and I will use that board to understand this particular concept. To begin with, we will start the discussion of the pin details of the LCD. LCD consists of the total 16 pins as I have shown here. The pin number 1 is going to the VSS, pin number 2 is going to the VDD, pin number 3 is used for contrast control. Important pins in this particular application, these are the 3 pins, that is RS is a register select, that is maybe control register or maybe data register. Read write, it is used for reading and writing purpose, and this enable, it enables the control signal or control register data or data register things. Now here the data pins, which are pin number 7 to pin number 14, and then pin number, that is anode and cathode of the LEDs, these are used, but mainly interfacing of the LCD, these connections are made. Some pin diagrams I will discuss in that particular case, but important thing is that whenever we are sending the command, this RS signal must be 0, means this RS signal, it should be 0 when we are sending the command, and the input applied to this particular pin is 1 when we are displaying the character or data. In case of the read write, 0 for writing and 1 for reading. Most of the times LCD is used in the writing mode. Sometimes whenever we are reading the busy signal of the LCD, in that particular case we will check its value, and in that particular case we will take its data from the pin number, that is D7, which is the busy signal. Now here we have the important enable signal. It has to be initially low for a certain period and then it has to be high for a certain period. This we should have the low to high pulse. In that particular case, the command may be transmitted or maybe the character may be transmitted depending on this signal, that is write signal is 0, and whatever the data we are putting on the D0 to D7, it will be given for the write operation, and this D7 is used in the read mode for reading the completion of the current operation, that is busy signal we are able to check through that particular pin. But generally we are using the LCD in write mode majority time. Now here some important commands. I will not discuss that much. You can use any website. You will be able to get the commands, that is 01 for the clear display, 02 for the return home, and so on. These are the available commands. I will use those commands which are required in our application. I will discuss those in detail. Then these are also few commands. Here the next is the character to display. What data we have to transfer. Suppose I am planning to display the character which is G, suppose initially. If I am planning to display this G, here this is MSB, which is 0100, that is nothing but hex number, it is 4. This is the hex number 4, and its lower nibble is, that is 0111, that is 47 hex character we need to transmit on the data pins to display G character. Then H and so on I will discuss further while I will go to the programming portion of this particular case. Now here LCD is used in the 2 modes, that is 8-bit mode and 4-bit mode. Whatever the FPGA board I am using, the interfacing of the LCD which is available with me, it is in the 4-bit mode, but I will discuss few things about the 8-bit mode also. While sending the command in the 8-bit mode, while sending the command in any mode, this RS, that is register selection, should be 0, because RS is a 0, in that particular case command will be sent, and when RS is equal to 1, in that particular case we are sending the data. This is read write, it should be 0 because we are writing to the LCD, means these two things are mandatory whenever we are displaying the data or we are sending the command to the LCD. Now here in this case I have some flow I am using here. In this particular case I am sending the command 38H, that is hexadecimal, that is it will initialize the 2 lines, then 5x7 matrix, and then 8-bit display mode, and we are using the D0 D7 line. We have to make E is equal to 0, that is enable pin must be 0 for 40 nanosecond, and then it should be 1 for 230 nanosecond. In that particular case this command will be processed by the LCD, or maybe more than that. This is minimum requirement. And this is the initialization command. Then if we are using the shift cursor to the right command, and its value is 06H. Again, in that particular case, E must be 0 for 40 nanosecond, E must be 1 for 230 nanosecond, and so on. Then we are using the command that is clear display, display on and cursor off. In that particular case, we are using the command which is 0CH, and it should be available for E is equal to 0, 40 nanosecond, and E is equal to 1 for 230 nanosecond. Means this enable pin, if it goes from the low to high, in that particular case, the low period minimum requirement is the 40 nanosecond and high period minimum requirement. This period minimum requirement is nothing but that is 230 nanosecond. It may be more than that, but it is minimum requirement, and so on. Then here we are sending the next is 01, that is clear display. Again same thing, E is equal to 0 for 40 nanosecond, E is equal to 1 for 230 nanosecond, and finally we are sending the command ATH, which will cursor at the first line and at the first character. Means it is at the beginning of the first line. Then again we are sending the E is equal to 0 for 40 nanosecond and E is equal to 1 for 230 nanosecond. That is the function or role of the enable signal. It must be low for 40 nanosecond and it must be high for 230 nanosecond to process the things. I will discuss in detail these things in the timing diagram. At that time I will recall these things. Now here suppose we want to transmit the characters, this character GHRITP, and we want to display it on the LCD. Then initially we worked on the commands, now we are working on the data. Now here in this case RS must be 1 now, because RS is equal to 0 when we are sending the command and RS is equal to 1 when we are sending the data. This RW, that is write signal, must be 0 again in both cases, in case of the command as well as in case of the data. Now here I am planning to display that is a G, which is 47H. Again E is equal to 0 for 40 nanosecond, E is equal to 1 again for 230 nanosecond. Then I am sending the H, then I am sending the R, and so on. For every case the enable pin must be low for 40 nanosecond and it must be high, that is 1 for 230 nanosecond. This is minimum. The same thing I am using. I have used here GH, R, this is I, E, this is T, and finally P. This I am planning to display in the 8-bit mode. But here this is, I am not interested more in 8-bit mode. But whatever the board, FPGA board I am using, it consists of the 4-bit mode. That's why I will discuss about that. Now here, this is the interfacing diagram which is available for the board which I have selected. It is already, these connections are made. So here the FPGA clock is available on the pin number C9 of the FPGA, reset is available on the pin number L13. Then RS pin is connected to the L18, read write pin is connected to the L17, enable is connected to the M18, and here in this case it is using the 4-bit mode to save the number of pins. That's why we are not using the D0, D1, D2 and D3, but we are using D4, D5, D6 and D7, these pins, and these pins are connected to the R15 of the R15 pin of the FPGA, R16 pin of the FPGA, P17 pin of the FPGA and M15 pin of the FPGA respectively. And here whatever I have shown the diagram here, this is the actual view which is available on the board. These are the knobs and these are the switches and this is the LCD, and internally these connections are available. Now here if we are sending the command in 4-bit mode, how it is, that is important. Now here whatever it may be the mode, it may be the 8-bit mode or 4-bit mode, this RS signal must be 0 and RW signal must be 0 to send the command. Is RS0 means we are selecting the register which is command register, and RW0 means here in this particular case we are planning to write the data. Here the hex code for initialization of this 4-bit mode is 28H. It is 2 lines, 5x7 matrix, and its display is in the 4-bit display mode. Now here in this mode data lines D4 to D7s are used as I have shown in the diagram. Now here how the data transfer takes place. I will go to the timing diagram, I will discuss in detail. Now we are planning to send the command 28H. This is 38H in case of the 8-bit mode, but in case of the 4-bit mode this command will become, that is 28H. That is 2H is the upper nibble. We have to transmit this first because this 2 is a hexadecimal number, it is 4-bit. And our configuration is a 4-bit mode. That's why we have to send this command. For this, sending this command on the data line, that is D4 to D7, which is the 4-bit, we have to make enable is equal to 0. We have to wait for 40 nanosecond. Enable is equal to 1. We have to wait for, that is 230 nanosecond. And after the transfer of MSB of the command, which is most significant nibble, we have to wait for 1 microsecond. Means 1 microsecond is the delay required in case of the 4-bit mode. This is not applicable to the 8-bit mode. In case of the 8-bit mode, we can transmit this, and I will discuss how will be the second byte. Now here 1 microsecond delay is required between upper nibble followed by the lower nibble. Here I am sending this upper nibble, that is 2 first. Then we need the delay of the 1 microsecond. Then after that delay, LSB command, which is 28 is the command, and 8 is the LSB nibble or least significant nibble of this particular command, that is 8H. Then after that particular delay, again we need to have E is equal to 0, which is for delay of the 40 nanosecond, and E is equal to 1 again, which is the delay of the 230 nanosecond. After that, we have to wait for 40 microsecond before sending of the most significant nibble of the next data. It's what we have done. Suppose this is the command 1 and this is the command 2. Is it right? This command 1 consists of the 2 nibble. That is, most significant nibble is the 2, least significant nibble is the 8. Here we are sending this command initially with E is equal to 0, delay of 40 nanosecond, E is equal to 1, delay of the 230 nanosecond. And then here is the delay of 1 microsecond. After that, we are sending this again, that is 8, that is lower nibble, again followed by E is equal to 0 for 40 nanosecond, E is equal to 1 for 40 nanosecond, and delay of the 230 nanosecond when E is equal to 1. And then while sending the next data or maybe the next command, this delay between the 2 bytes, it must be the 40 microsecond. That is the requirement in case of the 4-bit mode as well as in case of the 8-bit mode. But in case of the 8-bit mode, we will send this complete command at a time followed by 40 microsecond, and we are able to send the next command, and so on. LCD communication waveforms in 4-bit mode. Now here initially we will transfer upper nibble followed by the lower nibble, and the delay between the upper nibble and lower nibble is 1 microsecond. Similarly, after transfer of this complete 1 byte, that is upper nibble plus lower nibble, we should have delay of the 40 microsecond, because here is the next byte of the maybe command or maybe data. In this case again, this is the upper nibble and here it will be the lower nibble. Now I will discuss about the things in details about any of the single upper nibble. Now here, suppose this is the upper nibble, it may be something here in this particular case. Suppose this LCD RS, that is register select, it should be 0 whenever we are transferring the command or transmitting the command, and it should be the 1 when we are transmitting the data. And the valid data will be available. Suppose I am taking the example of the sending of the command. The command for the 4-bit mode, initial command for the 4-bit mode is a 28H, and this is the valid data which must be available on this particular line. Then here in this case, the LCD read write this terminal, it should go low because we are writing onto the LCD. That's why it should go to the low. Now look at this LED enable signal carefully. Now here this signal must be initially low followed by the high pulse, and the duration of this low period, it must be of the 40 nanosecond, followed by this is high pulse and its duration must be the 230 nanosecond. This is minimum requirement, and this transition period again it must be of the 10 nanosecond. Means these are the minimum requirement, and whenever we are transferring, this is upper nibble, this complete procedure has to be done. After that we should give the delay of the 1 microsecond. Then again the same process should be repeated for this lower nibble, which is again something like this. Then again we have to give the delay of the 40 microsecond. Then again we are transferring the upper nibble followed by here delay which is of the 1 microsecond. Again we will use the same procedure, and in this way we are able to transfer you are able to transmit the command or data to the LCD. Now this is about whenever we are working on the microcontroller, writing the program for the LCD is quite simple, because the most of the things will be handled by the controller itself. But as far as the FPGA is concerned, we have to do everything. Means controller should be designed by us only. Now here, whenever we are working on the interfacing of the LCD with the FPGA, we should have the three state diagrams. One is the power initialization. I will go through the state diagrams first, and then I will discuss about the role of these state diagrams, and then I will go to the programming. This is power and initialization. The second is the display state. This is the main state diagram, and finally we have, this is time constraint state diagram. These state diagrams I am using for understanding the concept of the how we are interfacing the LCD with the FPGA. Now here I will start with this diagram. Now here, whenever the state, init state, the finish LCD initialization sequence. Here yet it is not, because this care has to be taken by the state diagram, which is 1. Means whenever the power initialization is done, then 1, then we can go to the next. Otherwise, we will remain in this state diagram itself. Now here, whenever initialization has been started, now I will go to the previous state diagram, that is state diagram number 1. Now that is power initialization. Now here in the state diagram 2, if init is equal to 0, it will remain in the idle. If init is equal to 1, means we have initialized the state in the state diagram number 2, which is the main state diagram. Then if the init is equal to 1, until it becomes done in the state diagram 2, it will remain in the init itself. Now here, this is the command. Generally this is power and initialization. This process is provided by the manufacturer. I am using the Spartan 3E of the Xilinx FPGA. They have provided, they have the user manual, and user manual they have given the steps. Now here, whenever initialization is equal to 1, then we have to wait for 15 milliseconds. Means the board which I am using, it has a clock frequency of the 50 megahertz. That's why I need to wait for this much clock cycle. Then it will go to the next state, which is nothing but the 1. In this particular state, we will make SFD is equal to, this is 3H we are transmitting, we are making it as enable is equal to 1, it will remain for the 12 clock cycles. Then enable is equal to 0, it will remain for this much clock cycles. Means these are the steps given by the kit manufacturer, and we have to follow the user manual given by the manufacturer, and when it becomes 1, we are active in the state diagram number 2. Now here I will go for the state diagram number 2, that is display. Whenever this init is activated, the power initialization process will start, and whenever this power initialization process, initialization done 0, it will remain, and it will complete the power initialization process, and whenever the power initialization process has been completed, it will come to the next state, which is the function set. This is function set, then we have the entry set, then we have the set display, then we have the clear display, then we have the pause, then we have the set address, and then we are displaying the characters. Here I am using the character G, this is H, this is R, this is I, this is E, and this is T and P finally, and it will remain in this state itself. Now how, I will discuss in meantime. Now here for function set, we are sending the command. Now we are working on the command because data sending start from this point onwards. These are the steps I am using for sending the commands. Now here this RS register select must be 0, and we must have write and read terminal WR. This should be again 0 because we are writing. We are sending the command. Now here the byte which is 28H is the command for set function. For function set, the command is the 28H. Now here in this case, this we are working on the 4-bit mode. This 28H cannot be transmitted in a single byte transfer. Now here how is the case? Initially we will transmit the 2H, that is upper nibble, and then we will transmit the 8H, that is the lower nibble, as I discussed in the timing diagram. But how this will work in the program? Now here for that purpose we need this particular timing constraint. Now initially we have to activate Tx init is equal to 1, transmission initialization. This is 1. If it is 1, when it will be 1? I will go to the previous state diagram. Now look at here. Whenever we are doing the function set, we are using this particular command, rs is equal to 0. We have given this particular thing on the transmission byte. Now here, out of this, initially the 2 is taken. That is MSB of the particular byte, or most significant nibble of that particular byte. And then we will come to this particular state diagram. Then it will make high setup, that is E is equal to 0 for 2 clock cycles. That is nothing but 40 nanosecond. Then high hold, we will make it as the data is available on this. Then we will make it as enable is equal to 1 and we will wait for the 12 clock cycle, which is 230 nanosecond. Means here, this is the low pulse followed by the high pulse. This is high setup is the low pulse followed by this hold, that is high hold is nothing but 12 clock cycles. Then we are waiting for 1 microsecond. We are waiting for 1 microsecond because as I discussed in the timing diagram, if it is a lower nibble and this is the upper nibble, and here this is 8, this is 20, this is 2 and this is 8. Now here delay between these two nibbles, it must be of the 1 microsecond. This is 1 microsecond. Then 1 microsecond delay will be provided by this particular state. Then again we are transmitting this lower nibble, which is the 8, that is low setup. Again enable is equal to 0. We will wait for the 2 clock cycle, that is nothing but the 40 nanosecond. Then again this high, that is E is equal to 1 and we will wait for the 12 clock cycle, that is nothing but 230 nanosecond. And then after completion of this whole process, before transmitting the next byte, we have to wait here. We have to wait, and that wait is nothing but 40 microsecond, which is nothing but 2000 clock cycles. We have to wait for the 2000 clock cycles and then 2000 clock cycles, and then we will come to the done state and we will remain here itself, because that will make the transmission initialization is equal to 0. Now here in this way, I will come back to the original state. In this way, this function set command will be executed. Then it will come again into the entry set mode. In the entry set mode, again this will become 0, then tx initialization, that will become 1. Then we have to send a command which is 06. Again here for this case also, again we have to go to the state diagram. In that particular case, the tx init will become 1. Then high setup, that is nothing but E is equal to 0 for 40 nanosecond, then E is equal to 1 for 230 nanosecond, then it is a delay of 1 microsecond, then again E is equal to 0 for 40 nanosecond, and E is equal to 1 for again that is 230 nanosecond, and there is a delay of the 40 microsecond, which I was discussed in the previous slide, which is here. Now look at here, this delay between the two timings or 2 bytes will be of the 40 microsecond, that delay we are providing by that particular state. Means whenever we are going from this one state to the other state, in that particular case, this timing process will be followed. That is timing constraint, we are following the timing constraint. Means this state diagram is for timing constraint, and same thing will be repeated again and again. Just I will go through this particular slide. Now look at here. Then after entry set, we have to set the display. Its command is 0ch. Again 0 is transmitted first, then C is transmitted, and then so on. And we are completing the command up to this. After that, we are sending the data, which is Z. Now look at here, this RS. This register set, we have to make it as 1. And whenever we are making this register set as a 1, its data will be the 47H. In this particular case, we are sending the 4H, that is upper nibble, followed by the lower nibble as mentioned in the timing diagram. And for that particular, we are designing this particular state diagram, which will help us to follow the timing constraints. Now I will discuss about the LCD interfacing program. I have created the module tutorial 4. I have selected this device, that is XC3S500E with package FPGA320, and I have created the module, that is LCD. Here I will discuss the main program. Here this is the library declaration part, this is entity declaration part. I have selected only the two inputs, that is one is a clock and reset. Whenever reset is equal to 1, it will remain in idle state, and whenever reset is equal to 0, it will process and display the character. This SFD terminal is used for it is 4-bit, and it is connected to the input of the LCD pins and data pins in the 4-bit mode, and it will send the data as well as command to the LCD in the 4-bit mode. This is LCD enable, this is LCD RS, that is register select, this is LCD read write, this is SFC0, it is used for selection of the star flash of the LCD, and this is data display, it is used only during the waveforms. It is not actually playing any role as far as the displaying of the data on the LCD is concerned. Now this architecture consists of the mainly 3 state diagrams, which I discussed in the during the slides. Here the first state diagram is init sequence. It will create the initial sequence, which is it will go through the state, that is idle, then 15 milliseconds, 1, 2, 3, 4, 5, 6, 7, 8, and then done. Whenever done is there, then initialization will be completed. And here I'm using the state signal, which is init state, and I'm using the counter here, which is I, which is 0 to, that is 7,50,000 integer value. Then here I'm using the second state in this particular case is the display state. In this particular case, we have the init function state, then entry state, then set display, then clear display, pause, then set address, and displaying of the character, which I am using C, H, R, I, E, T, and finally P, and whenever it is done, it will remain in this particular state. Then the third state diagram which I am using, that is nothing but the time management, which is nothing but the time constraint. Here in this particular case, we are using the high setup, then we are using the high hold, then we are using 1 microsecond, then low setup, then low hold, then 40 microsecond, and then done. It will repeat it for every 8 byte of the data, or maybe command transmitted to the LCD, because we are using the 4-bit mode. In that particular case, it should be repeated every time. Then it's a state signal, which is nothing but the TX state. Now here I will begin with the program. Now here SFC0, we are disabling the star flash, and the LCD read write is equal to 0, because we are using the LCD only in the write mode. That for that purpose we are using this. Then here during the power initialization state, it is begin. Now here if the reset is equal to 1, then it will remain in the initial state. Otherwise at the edge of the clock, it will follow the init state. Now what is the state? Now here it will come into the idle state by default whenever reset is equal to 1, and when init done is equal to 0, means initialization has been not completed. Then in that particular case, it will remain in the initialize the initial value. Init done is equal to 0. Now here look at init underscore init is equal to 1. Then it will go to the next state. It will go to the next state in this particular case. And where we are initializing this, we are initializing this particular signal in the main state diagram, which I will show here. I will go to the main state diagram. Here, when we are using the main state diagram, reset is equal to done, it will be current state will be the init state. This is main state diagram. We will be in the init state. And here, whenever reset is equal to 0, we will come to the current state, and that is nothing but initial. We are making initially transmission is equal to 0 max 1, then init underscore init 1. This means whenever we are coming in this state and whenever this value is 1, then power initialization state will be started. And look at here itself. Look at here itself. Whenever if this initialization done, power initialization done is equal to 1, then it will go to the function state. Otherwise, it will remain in the init state itself. Means during this init state itself, the power initialization state diagram functions must be completed. I will go back again to the power initialization state diagram. Now look at here again. If init is equal to 1, this init is 1 in the main state diagram, then we will move to the next state, which is the 15 millisecond. We will wait for the particular period. Throughout this power initialization process will be completed, and during that particular case, module must be in first state itself, that is init state itself. Means here, whenever it is in this particular state, until this done will become 1, and whenever the power initialization will complete, look at here, initialization done is equal to 1, it will become in the done state of the power initialization, and when this is completed, then it will come into the next state, which is nothing but the function set. Now here, during the function set, this init is already 1, this mux is 0, then this is 0, then this rs is again 0. Now here, these are the functions, these are the values we are setting. Now look at here, if I2 is equal to 2000, then the current state is entry set, which is the next state. Otherwise, it will remain in this state itself. Now what is this I2? I will check it out. This I2 is controlled by the third state diagram. I will go to the third state. Now here in this case, what it does, it will make the high setup, and here LCD enable is equal to 1, SFD is equal to, now look at here, it is taking TX byte, which is 7 down to 4, that is a 4 bit value, which is MSB of the total byte or most significant nibble. LCD enable, now here LCD enable is equal to 0 here, and then LCD enable is equal to 1 here, and again the data is the same, that is MS, that is most significant nibble, and here we are waiting for 230 nanosecond, and then after that we are waiting for the 12 clock cycle is nothing but 230 nanosecond. Then we are going here, and here we are providing the delay of the 1 microsecond, which is the delay required between the first nibble and the second nibble, that is MSB nibble and most significant nibble and the next nibble. Now after that delay, we are moving to the next state, and look at here, now we are making the LCD enable is equal to 0, and look at the data. Now here SFD0 is a TX byte, which is 3 down to 0. 3 down to 0. Means here in this particular case, we are transmitting here the least significant nibble. Suppose I have the command which is the 28H. During the first process, we have processed this. Now we will process this LSB, that is least significant nibble. And in that particular case, here initially this LCD enable is equal to 0, we have the lower nibble. In that particular case, we are waiting for the 2 clock cycle, that is nothing but the 40 nanosecond, and then we are making this LCD enable is equal to 1, the data is the same, and then we are waiting for the 12 clock cycle, which is nothing but the 230 nanosecond. And after that, we are providing the delay of the 40 microsecond, and the 40 microsecond is nothing but the 2000 clock cycle. And here this I2 will reach to the 2000 only in this state. Otherwise, it will be sometimes it may be the 2, its value will be the 12, and then because in the next state we are initializing its value as 0, and finally it will come to this 40 microsecond state, and after that it will come into the done state, and whenever it will come into the done state, we have to go into the initial state itself. Now look at here, I will come to the main state diagram again with the first state, which is the function set. In this function set, we are trying to transmit this value. Initially 2 will be transmitted, that care is taken by the time constraint state diagram. Then we are transmitting this 8 because TX byte we are putting on that, then it will select upper nibble and then followed by the lower nibble, and when its value becomes 2000, the value of the I2 becomes 2000, it will go to the next state, which is the entry set. Otherwise, it will remain in this particular state itself, and this value will become 2000. I2 is controlled by the third state diagram, which is time constraint state diagram, and when it becomes 2000, it will go to the next state, and so on. Now here in this case also, if we are going to the entry set, we are initializing some values here, because this is the Murray machine kind of the things. Its output will depend on the present state only. Means if we are coming to the present state, these are the values we are going to assign. And again here, if I2 is equal to 2000, then it will go to the next state. Means this I2 is a 2000. This 2000 value of the I2 will be there in the third state diagram, and which will carry out the two steps. That is LCD enable is equal to 0, which is nanosecond. Then LCD enable is equal to 1 for 230 nanosecond. This is for the transfer of the MS nibble. And then again, this value is 0 for 40 nanosecond and 1 for 40 nanosecond. And then it will remain this value for 230 nanosecond, means it will transfer the LS nibble, that is least significant nibble. And here it is performing the most significant nibble transfer. And the same process is repeated again and again in every state diagram. Then set display, then clear display, then pause, then set address. The same process or same constraint timing diagram is will be followed. Now look at here. If I am coming to the data transfer, this is again 1. Then look at this value, RS, register selection. Now this value is 1. Now we are transmitting the data which is 47H, and during this 47H, the first 4 is transmitted by taking the help of the third state diagram, and then we are transferring the 7 by using the same, and the time taken by this is controlled by this counter I2. When the counter becomes I2 is equal to 2000, it will go to the next state, because this I2 will become 2000 only in the done state of the timing constraint state diagram, and the same sequence we are following here. Now here I will come to the simulation. Here I will simulate behavioral model. Here I will add few more things to the wave window. In its state, I will add this to the waveform window. Its counter I will add. Then I will add then this current state. Then its counter, which is I3, I will add here, and then finally I will add the TX state to this window, and its counter, which is the I2, and I will reset it and I will relaunch it. Now here I will make few changes. It is unsigned disable, and this predicts, we will make it as ASCII. And now we can observe its waveforms. Now these are the waveforms. I will discuss each point one by one in detail. Now look at the first state. This is the init state, and look at this init state. This will complete the initialization, and whenever the initialization has been completed, it will move to the next state. Here the states are shown here. I will just zoom it, and I am able to show all these states whatever here, and available data transfers and all those things. Now here, if I am zooming a bit, I will zoom the portion which is close to here, and I will show something here. And here after 2, 4, 8, and done. And whenever done, power initialization has been done, the main state diagram, which is this, that is display, it will go to the function set and then entry set and so on. Now here for function set, this is the third state diagram, which is timing constraint. Now here for function set, what are the things are completed that I will show. I will zoom it properly. Now here during the function state, I will start from here. The function state is started from here. Just I will zoom it. Now here it has been carried out the things which I will show from here onwards. Here done. Then this is high setup. This is high hold. Then it is waiting for 1 microsecond. I will minimize it. Then after waiting for 1 microsecond here, it will come to this. I will again zoom it properly. I will go to this part. Here I will zoom it further. Then again, this is low setup, low hold. And after that, low setup, low hold, then we are waiting for 40 microsecond. And after completion of these states, 40 microsecond. After completion of these states, now look at this is, I am minimizing this 40 microsecond, it will come here. And then done will be there, we will enter into the next state. That is entry set, then this entry set will be completed, then set display, then clear display, then pause. And after that pause has been completed, I will show here, this is the pause. I will minimize this. Then I will come here, and from here the command transfer has been completed. Now the data transfer will take place here. And we are planning to display the character, that is GHRITP we are displaying. Now here I will zoom this portion, how the character G is transferred and so on. I will show this. Now here G is a character. It is a 47H. This 4 is the higher nibble and 7 is the lower nibble. How it will be transferred, that I am trying to show here. Now here in this case, whenever the data line will select that is a 4 in that particular case, this is high setup, which we are making E is equal to 0 and we are waiting for 2 clock cycles. Here that is nothing but we are waiting for the 40 nanosecond. Then we are making E is equal to 1 and we are waiting for here high hold, we are waiting for that is 230 nanosecond, that is 12 clock cycles. After that, before transferring the lower nibble, we are waiting for 1 microsecond, which is shown here. Just I will minimize it. We are waiting for 1 microsecond. I will come here. And after that 1 microsecond, we are transferring the lower nibble. In that particular case, here I will zoom it again. The low setup means we are transferring, we are making E is equal to 0 and we are waiting for 40 nanosecond. And again here we are making E is equal to 1. And we are waiting for the 12 clock cycles and 7 is the lower nibble. After that, we are waiting for 40 microsecond. This is, we are waiting for 40 microsecond. Just I am minimizing it. I am minimizing it because difficult to show the waveforms. We are waiting for 40 microsecond here. And after that, the next character will be, character transfer will take place, which is H. And so on. Just I will minimize it to show all the characters here, and the characters available are GHRITP, and in this way we have simulated its output. Now here what I will do after the simulation, I will synthesize the code and I will dump the code into the FPGA and we will see this, the same thing GHRITP on the FPGA board. Again I am coming back to the implementation part. Here I have given the pin constraint. Here that is UCF pins are given, and now I have already synthesized it. I have completed the implement design, then I have completed generate programming file, and now I will click on the configure device impact. I will click on OK, then it will detect my hardware. Now here it has created the file, then I will click on the boundary scan. I will add the chain here, then I will program this here, the tutorial 4 and this lcd.bit file. Now I have made all the connections to the Xilinx board. This is the data cable which I have connected to my laptop, and it is connected to this B type of the connector, and this is a power cord. I have connected it to the supply mains, and finally I will program the device, and it will display the characters GHRITP, and you can observe, now look at here, the characters which are GHRITP are displayed on the LCD.